Hello. So we continue with our previous module, and we had asked the question like, how do we generate an electromagnetic waves, EM waves, EM waves. So as we can see, it's a combination of electric field and the magnetic field that makes an complete EM wave. And we would see right now here in this slide how we are going to generate an electric field. First, we will see how an electric field can be generated. So it is indicated by an E. So let's say we have this positive charge and we have this negative charge. So what we know that there is a positive charge sitting here indicated by this sign and the negative charge. So in between them, there'll be a electric field, generation of an electric field. So I have shown it in the with one single arrow. Okay, and then arrow pointing from positive to the negative. So we also say that there is an electric force that gets generated between these two charges, which are of opposite polarity, and we generally indicate the electric field with the vector, because vector means is vector. It means it has a quantity, it is a quantity with direction and the magnitude. Okay, with direction and magnitude. And scalar, on the other hand, it is only with the magnitude. Okay, so you see that we have this electric field component, and we can show that with this arrow, or we can also use this kind of representation. So remember that. So we see that this positive charge and the negative charge, there is an electric field line. We can show it that. Now let's say these charges are moving, the positive charge coming down and the negative charge going upwards. So at some point in time, there'll be a situation like this, that the positive charge is trying to go down, negative charge is trying to go up, and they are very close to each other. So in fact, we can say that electric field between them is zero. And another instant of time, we see that the negative charge has gone up and the positive charge has gone down. And again, the electric field will be large between them as indicated by this arrow, and it is again pointing from positive charge to the negative charge. So you see that there is an oscillating behavior. So you see that the electric field is maximum at this instant, then electric field is going down up to zero, then again electric field is going up up to this instant. At another instant of time, so let's say this is time t equal to 0, t equal to 1, t equal to 2, and so on. So now at this point, at t equal to n second, let's say, we again have the negative charge trying to come down, positive charge trying to come down, and they come so close to each other so that again the electric field is 0. And finally, at t equal to, let's say, n second, n plus 1 second, again, the positive charge and the negative charge comes like in this position, and the electric field is again maximum. So you see that we can say that the electric field is now coming down like this. Okay, it is going to be going down and up to 0. Again, then electric field is trying to maximize itself, and it goes like this. So you see, it's basically an oscillating pattern. So we see that if you want to draw it like this, so let me draw. It is all ink like this. So if it is like a time axis, this is t, and this is like, say, this is an amplitude or magnitude of an electric wave. So I will see that at this point in time, I have an electric field at a maximum. At this point in time, the electric field is 0, right? At this point in time, the electric field is maximum again, but this electric field is in the negative direction. Again, at this point in time, it is passing through 0. And again, at this point in time, I have this component like this, and so on and so forth. So you see that this is how I can say that electric field can be generated. And you can point in all those directions of arrows to show the magnitude of the electric waves. Electric waves. So this is your electric field, indicated by vector E, like this, or you can use like this. Remember, vector is a quantity with the direction and the magnitude. Now we have understand we have understood how we generated an electric field. Let us have a look at how a magnetic field will generate. So let us have an example of this. I have this wire indicated by the gray rod, or let's say it's an antenna, and I have a current flowing through this wire indicated by this arrow, and I have denoted it with the symbol I. So arrow is pointing in the upward direction. So I can easily say that my positive charge is sitting here and negative charge is sitting here. And the positive charge is pointing towards the negative, is trying to get towards the negative charge, or negative charge is trying to get towards the positive charge, because there is a force of attraction between the two. We can see that, we can refer the Coulomb's law. So when such situation occurs, so we say that there is a rod or antenna or a wire carrying an electric current I, the direction of which is shown as by the arrow. Due to this action, there'll be a creation of a magnetic field. You see that, a magnetic field. And the direction of that magnetic field would be indicated by this arrow. So you see that whenever there is a current going through a wire, there will be a magnetic B field gets created, indicated by B. We can again represent it as a vector B, like this or like this. So how to understand this concept here? So again, use your right hand. Imagine you have this current carrying wire. Direction of arrow shows the current direction, and right hand, we will use the right hand rule that shows that. So use your thumb to show the direction of the current flowing through the wire, and rest of your fingers acts as a coil. You see that, as indicated by in this picture. So direction of the B field that gets generated will be indicated by your rest of the fingers. So you use this picture to understand that. Second situation, let's say I have the current flowing through the direction, through the wire in this direction, arrow pointing downwards. So again, I am assuming that the current flows from the positive charge to the negative charge. Okay, and there is an electric field between them. Now, because of this current flowing through the wire, I will have the component of magnetic field B. So, and that direction of the magnetic field will be indicated by this circle. You see the arrow here. You see this arrow. How to understand? And again, use right hand rule. Right hand rule. Show your thumb pointing downwards, that indicates the direction of current, and rest of the fingers, they are wrapping around this rod or wire or an antenna to indicate the presence or creation of the magnetic field component. So again, if we want to indicate both electric field and the magnetic field in the same plane, so let's say I have this an electric field like this. I call it as an E field, and I will show it through the arrow. So arrows showing the strength of an electric field with respect to time. This is your 0, okay? And this is EM wave. So where is the magnetic field component now? So we can actually show that. So magnetic field component would be out of this plane. Out of the plane means I am showing you this concept on this slide. So I can draw like this. I can draw like this, like this. So this is my B component. Okay. So you see that the electric field and magnetic field, they are perpendicular or orthogonal to each other. And this combination is perpendicular to the direction of propagation, which is in the z. So let's say we have z direction, this would be x plane, then there will be a y plane like this. So you can actually show that component like this. Okay, so if no, this will be y, this will be z. So if let's say out of plane is the y plane, your magnetic field is coming out of this slide and going into the slide. X is the electric field which is going upwards and downwards, indicated by the red color, and the z is the direction of the wave propagation. All right, so we move on to the next concept,